Okay, the static electricity post-assessment, I'm going to give you some hints and strategies to follow as you take that assessment, and just pause the video as you need to. Starting with question 1, we've got two spheres. One's got a charge of +1 and one's got a charge of +2. Both of these spheres are positive, which means that they both have a deficiency of electrons. But one of them tends to have more electrons than the other. And electrons are always going to flow to an area where there is less electrons. So the electrons are going to flow from an area of a high concentration of electrons to a low concentration of electrons. We can eliminate A and B because protons never move. They are stuck in the nucleus. So your answers are going to be out of C and D, and you're going to choose the answer that corresponds with more electrons flowing to an area where there are less electrons. But both of them have a deficiency. Okay, number 2. It says an alpha particle is released above a positively charged plate. And they say the alpha particle consists of 2 protons and 2 neutrons. So we've got 2 protons and we have got 2 neutrons. Neutrons have no charge. Protons, have a positive charge. So if you've got 2 positive charges and 2 neutrals, this alpha particle is positive. And there is a rule that says that unlike charges attract and like charges repel. So if the alpha particle is positive and this plate is positive, it's going to tell you something about the way that particle is going to move. Number 3. The electrical field strength between 2 parallel plates that are 42 centimeters apart is 840 volts per meter. What is the potential difference between them? I'm going to quickly go to your reference table, which you should have handy anyway. Let's just quickly look at some constants and equations that you're going to need. We're going to need Coulomb's law constant, which is 9 times 10 to the 9. And we are also going to be looking at Coulomb's law. And the equation we're going to use now is E equals V over D. E for electric field strength, not energy, equals voltage over the distance. And this is when we're dealing with parallel plates. So if I apply this equation here, E equals V over D, and they're telling us the E is 840. We need to know the V, the voltage or potential difference. And the distance they're telling us is 42 centimeters, which is going to go here, but we're going to convert that to meters. It's going to be 0.42 meters. So we've got meters here, we've got volts over meters over here. You can see meters are going to cancel, we're going to land up with volts, but you're going to solve for V. Right, number 4. 2-point charges located 2.1 meters apart. One charge has one's got a charge of 4 times 10 to the minus 6 coulombs, and one's got a charge of 6 times 10 to the minus 6. What is the electrostatic force between the charges? So we're going to just use Coulomb's law. F equals K, Q1, Q2 over R, which is the distance between them, squared. And now we're just going to substitute. K is 9 times 10 to the 9. I just showed you that on the reference table. Then you're going to take these 2 charges and you're going to put them here for Q1 and Q2. It doesn't matter which is which. You're going to multiply those together, and then they are 2.1 meters apart. So you're going to do 2.1 and you're going to make sure you square it. So do the math and you should be able to come up with the answer. Number 5. A negatively charged metal rod is brought into contact with a neutral metal sphere. Which is a description of the charge of each object after contact? So we've got a neutral sphere, and we have got a negatively charged metal rod. It's got an excess of electrons. What I said earlier was that electrons always go from an area where there's a high concentration of electrons to an area where there's a low concentration. So if this sphere here is neutral and this rod is negative, the electrons are going to want to move onto that sphere. That sphere was neutral. Now that sphere is going to have some of these electrons. So some of these electrons are going to go away and they're going to go here. Which of these choices describes that scenario? Number 6. A student touches a negatively charged rod to an uncharged electroscope. Which is the result? Okay, so this is an electroscope. It's for measuring charge. It's got this gold leaf that can move when a charged object is brought close. When you bring a negatively charged rod close, okay, what's going to happen is, just like we had over here, the electrons are going to jump on here. And when those electrons jump on, this bottom area and the leaf become negatively charged. And because both of them are negatively charged, like charges repel, that leaf kind of deflects. But the key is that as you touch the rod to the electroscope, there's going to be a movement of electrons that are going to go down to this area. So see which scenario describes that. Which of your choices? Right, the last question, question 7. An electron loses 2.00 times 10 to the negative 15 joules of energy traveling to the screen of a laptop computer. Why is this energy loss so small? Well, let's have a look at the charge of an electron. I'm going to quickly go back to the reference table. A single electron has a charge of 1.6 times 10 to the negative 19. That is a very, very small charge. (1.6 times 10 to the negative 19 coulombs), and it's a negative charge. That's the charge of an electron. It's an extremely small charge. And as a charge moves, as charge flows, even when it's an electric circuit, energy gets lost by the charge as it moves from one point to another. It moves from a point of high potential energy to a point of low potential energy, but it does so, and as it does it loses energy, kind of like an object falling. So if we have a negative plate and a positive plate, for instance, an electron naturally is going to move down from the negative to the positive. It's got a lot of potential energy here, it's got a little bit of potential energy here, and as it does, it's going to lose energy. Just like an object falling through the sky is going to lose gravitational energy as it falls. But the key is this: the charge of an electron is extremely small.